Hello everyone. In this video, we are going to discussing about the deformation of uniformly tapering circular bar. So let observe in the diagram. Here, circular bar varying diameter uniformly. At end A having the diameter of the D1. At end B having the diameter of the D2. So where the D2 is greater than the D1. So now consider a uniformly tapered circular bar subjected to a axial force capital P, and the length of the bar is capital L, and having the diameter of the D1 at one end and the diameter of the D2 at the other end. So now we have to consider a very small section. So at the section XX, so which having the length of the dou x and the diameter of the dx, and this smaller section is placing distance small x from the end A. So here we are considering the very small section. So at the section XX, we are considering the very small section. So which having the length of the dou x and the diameter of the dx, and this small section is placing distance of the small x from the smaller end of the, that is end A. So now the diameter of the smaller section, that is the dx, equal to the, so d1 plus d2 minus d1 divided by L into x. Now the question is how this relation is came. So for this one, first I have to observe in the diagram. So here I have to observe that one, this is the diameter d1. So this is the diameter d2. So this is the d1 and this is the d2. So now this portion, this complete portion is d2 minus d1. So up to B2 to, and similarly from here to B. So this total portion is d2 minus d1. And the bar is uniformly is varying. So this portion is, only this portion is d2 minus d1 divided by 2. Similarly, same thing you have to observe for the smaller portion which having the diameter of the dx. Here also have to observe that one. So this is the diameter of the d1, remaining portion. So this is and this is, which is equal to the dx minus d1. So here bar is uniformly varying. So this dx minus d1 is also sharing equally at this portion. So then this portion will become, so dx minus d1 divided by 2. Here I have to observe that one, so here we are having the two symmetrical triangles, that is the AX1A. So AX1 which having the one triangle. Similarly AB2, it is also another triangle, and we have to observe that one, these two are the symmetrical triangles. Then we are applying the properties of the symmetrical triangles. Then so the length of the x1 divided by a1 equal to the length of the b2 divided by the a2. So we know that one, the x1 value, so which is equal to the dx minus d1 divided by 2, and a1 value also we know, that is the small x. So here I have to substitute x1 which is equal to the d2 minus divided by 2, and a1 value equal to the x. Similarly we know the b2 value, so which is equal to d2 minus d1 divided by 2, and a2 value also we know, that is the length of the bar, that is the capital N. Here also I have to substitute b2 values and a2 values, here I have to substitute. Then it will become, so dx minus d1 divided by 2x equal to d2 minus d1 divided by the 2l. Here 2 will get cancelled. Then so dx minus d1 divided by x equal to d2 minus d1 divided by l. So from this relation, we have to find out the dx value. So here dx value will become the d2 minus d1 divided by L into x. So just we have to send this x into the right hand side. From this one, we have to write down the dx value, which is equal to the dx equal to d1 plus d2 minus d1 divided by L into the x. And this equation once again I have to write down the dx equal to d1 plus kx. So where k equal to the d2 minus d1 divided by L. So now we have to find the deformation of this small section. So that is this dou x section. We have to find out this deformation or maybe extension. So here we are applying axial forces P we are applying. For these forces, we have to find out the deformation of this smaller section. So that is the dou x. So extension of the shorter length. So let us consider the deformation of the whole bar is delta. For the smaller section, we are considering the dou delta. So then the dou delta equal to, we know the deformation formula, that is the delta equal to PL by AE. So PL by AE. So here we have to find out the deformation of the small section. So that's why here, so delta will become the dou delta. So here load we are applying, that is the force we are applying the capital P, and length of the smaller section which is equal to the dou x, and the area. So this is the circular one. So let us consider the pi by 4 dx square. So into E value have to substitute. So here, so deformation or extension of this smaller section. So that is the dou delta equal to P L. Here L equal to the dou x, P dou x divided by so area which is the circular one, pi by 4 dx square into capital E. So now we have to find this extension or maybe deformation of the whole length of the rod. The whole length, which is nothing but summation of all the smaller section from the starting of the bar to the end of the bar. So which is nothing but, so we have to sum the deformation of the smaller lengths which is from the end of the, starting of the bar to the end of the bar. So which is nothing but delta equal to summation of all the smaller sections, summation of the extension of all the smaller sections, which is equal to the summation of dou delta. So where to where we have to add from the starting point to end point. So this is we have to write down in the terms of the x terms, which mean x equal to L mean, so at the bigger end, at the end of the bar. So when the x equal to 0, so this particular location is at the smaller section, that is the, also have to write down the x equal to 0. So now we have to add the deformation of the smaller sections from the starting of the bar to the end of the bar, that is when the x equal to 0 to and x equal to L. So delta equal to summation of x equal to 0 to x equal to L dou delta. And we know the dou delta value. So dou delta value equal to P dou x divided by pi by 4 dx square into E. Same thing we have to substitute here. So then delta equal to so which is nothing but summation is nothing but integration of where to where. So 0 to L P by pi by 4 dx square E. Let us consider this is the dx. So this equation once again I have to write down so 4p by pi dx square E dx. And we know that one so here 4p and pi E are the constants. So it is nothing but dx by 1 by dx square. So which is nothing but, so it is so and we have to substitute the dx value. So we know the dx equal to d1 plus kx. So this equation will become 4p by, so integration of 0 to L, 4p by pi into d1 plus kx whole square into E dx. Here 4p pi e, these are the constant. Then we have to get the outside from the integration. Then this equation will become the 4p by pi e integration of 0 to L. So 1 by d1 plus kx whole square dx. So which is in the form of integration of, so 1 by x square. So 1 by x square dx. So what is the formula of the integration of 1 by x square dx, which is nothing but minus 1 by x, 1 by x. Same thing I have to write down, but here x is in the form of the a plus bx. So integration of 1 by x square. So but here x is in the form of the a plus bx form. Then for the integration of, so 1 by a plus bx whole square formula is, so minus 1 by x minus 1 by a plus bx into 1 by derivation of this a plus bx. Same thing here. So we have to do the integration for 0 to L 1 by d1 plus kx whole square dx. So this is the 1 by x square formula. So minus 1 by x. Same thing here. So 4p by pi e. So minus 1 by x. X is nothing but, so d1 plus kx integration 0 to L. But here, so x is in the form of a plus bx. This is once again I have to write down the 1 by d by dx of a plus bx. Here a plus bx is nothing but d1 plus kx. So this equation will become the, so this integration equation, so it will become, so minus 4p by pi e, which is constant. So d by dx of d1 plus kx. So d1 is the, so constant, here k value will be get. So minus of 4p by pi e into 1 by k. So this is nothing but, just we have to substitute the limits here. 1 by d1 plus k into, in the terms of x we have to substitute L. So k into L minus of 1 by d1 into, so here we have to substitute 0 value. So this equation once again it will be become the minus 4p by pi e. K value we have to substitute. K value we know that from the d2 minus d1 divided by L. Same thing we have to substitute d2 minus d1 divided by L. And this one, so here also I have to substitute d1 plus k value d2 minus d1 divided by L. So d2 minus d1 divided by L minus of, it will become the 0. So 1 by d1. Here L will get cancelled, and also here d1 also it will be cancelled. Here only the 1 by d2 minus 1 by d1. So here, so L have to will get the here L. So then the 4p L by 4p pi e L by d2 minus d1. So here same thing we already saw, here d1 and also d1 it will be cancelled. Then 1 by d2 minus 1 by d1. So this equation will become minus 4p by pi e L by d2 minus d1 into 1 by d2 minus d1. So to eliminate the minus value, so this equation once again I have to write down the 1 by d2 minus d1 minus of 1 by d1. So this is what I have to write down the 1 by d1 minus of 1 by d2. So then equation will become 4p by pi e into L by d2 minus d1 into 1 by d1 minus 1 by d2. So here, so delta value is, which is, so deformation of the circular bar. This is the delta equal to 4pl by pi e d2 minus d1 into 1 by d1 minus 1 by d2. Then we have to solve this equation. So we will be get 4pl by pi e d1 d2. So LCM we have to take d1 d2 here, d2 here, d1. So this d2 minus d1 here, d2 minus d1 it will be cancelled. Then 4pl by pi e d1 d2. So let us consider, so we know the deformation of the, so circular bar. Let us consider circular bar. Here circular bar is not just not a tapering bar. Here d1 and d2 is equal, then it is the circular bar. Same thing, In this formula, I have to substitute d1 equal to d2 mean. So which is the 4pl by pi e d square. So we know this is also I have to write down the pi e by d square. Pi e by d square is nothing but area of the circular bar. So this is we know deformation of the circular bar is 4pl by a. So this is the solution of the deformation of the circular tapering bar. Thank you.